TTL Computer 2. Today, we're going to take a look at the printed circuit board design for our program counter. And we're going to just jump right on into this. So we're looking at our schematic for our program counter. I'm not going to go into this in great detail because this schematic almost exactly matches our digital design, or digital simulation design. So we have two 74 LS 245s that buffers our input for our control signals and for our data bus, and drives the local signals on our card. And we have our four 74 LS 161 counter ICs. And we have these two implementing the high byte of the program counter, and these two implementing the low order byte of the program counter. And you can see that the ripple carry out from each counter cascades up to the next counter, right? Ripple carry out to the next counter, ripple carry out to the next counter, right? So these both produce 8-bit counters. We have two 8-bit counters for 16 bits. Each of these are output through a 33 ohm resistor network, and that's we use that for impedance matching to the bus, as well as to eliminate ringing that may be on the lines. So we have the high order byte and the low order byte both coming out to the output bus. And finally, down here we have our card edge connector, and we can see here just a close view of our card edge connector. We have our data bus here. We have our output 8-bit output bus here. We have power and ground for the connector in its standard place. These signals down here are going to be the standard place on the card edge connector for our main control signals, which is going to be the clear signal, the not counter, the P counter, the U counter, and the T clock here. So we're not needing these signals on this card, so they're just blank. And then we have the rest of our control signals for this card: counter in low, counter in high, counter enable, counter out low, and counter out high. So that is our schematic for our printed circuit board. That's our first schematic for our active elements. And then we also have some passive elements, right? We have bypass capacitors that we use for most of our ICs. We have power decoupling capacitors for our board. And we also have a power indicator LED. Now, so just a couple things that I did here that differs from our digital design is that I reordered some of the input signals. This in our digital design was D0 here through D7. I switched them around to be D0 through D7 this direction. And I also switched around a few of the input signal ordering. And the reason why I did that is that to simplify the routing on the printed circuit board, to make sure that we don't have lines that are unnecessarily crossing each other that would complicate the routing. This way, when I do the digital design, I don't really have any understanding of what the final card edge and the routing is going to be. So it was just what logically made sense to me. But part of, again, doing the card design is tweaking some of those things, the ordering on some things, to get the trace routing to work in a good way. Okay, so that's our schematic. So we have the active and the passive elements. And then our printed circuit board is looking like this. Okay, and so we have our card edge connector down here. We have our 2 input buffers, the 245s here, and then our 2 output 245s here. And those are feeding into the, the 33 ohm networks, which are then feeding into the card edge. So we're taking the, the card edge inputs are coming in through these 2 ICs. I brought them up and around this way on our card. Here's our 4 LS 161s. Here, our counter ICs. Their inputs are pulled down from the bus lines above, and then our output signals, right, are coming down from our 161s and into our output buffers. Okay. So this card, again, I'm pretty much strictly just using all manual routing now. I'm not using automatic routing at all. So this card was a bit of a challenge to do the routing. This was my second go around at doing the routing. I did a first version, but I wasn't completely pleased with that. I had these bus lines coming down through here, and then I didn't like that because the lines, the output lines from the 161s as they come down here were crossing over all of the input lines, which I didn't like. Didn't seem like a good approach. So I brought the input bus lines above the 161s, pulled down, drop the inputs down to the 161s, and the outputs, right, come straight down into the output buffers. So you can see we have our our decoupling, our bypass capacitors, for each of our ICs. We have our power indicator, and our power bypass caps, 3 of them, one here, and one here. And let's see what else to point out. I think that's it. We could take a look at our 3D design for the board. Okay, that's our 3D design for our board. Right, our output elements, our input buffers, and then the 4 161s here. Right, and again, our power indicator up here. Okay, so one thing to note, that was the other thing I wanted to note, was that this is our program counter board. The memory address register board is substantially identical to this. The only thing that's really different between the two is that the output, rather than being 8 bits at a time, is going to be 16 bits. So when I did the layout for this card, I was keeping that in mind. So, right, so I wanted to make sure that this overall design would handle the 16-bit output. So we can see, the 8-bit output goes here, both the high and the low byte go here. But in the memory address register, this will be the low byte from here, and then the high byte will come out here, right? So we will have, 0 to 8 bits here, and then, 9 through 15 will be here as well. So I was careful to try and consider that as best that I could, such that once we get this back from fabrication and populate and test the board, it should be a quick turnaround to just modify this board to meet the design requirements for our memory address register board. So we're kind of getting 2 boards for one. And I'm hoping that I can kind of keep this footprint for the board. It's 200 millimeters by 150 millimeters. I'll try and use this size, kind of make that be the standard size for our other boards as well, and only go larger than this if we need to. So this way, most of the boards will be, try to keep the boards the same size. Our clock card is smaller than this, but I wasn't really trying to make them all be the same size. But if we can, I'll try and minimize the card size variance if we can. Okay, so I think that's it. All that I wanted to show you. The design came out pretty well. I'm pretty happy with it. And yeah, by the time you see this video, this should already be off to fabrication again. So I think we're moving at pretty good clip for our PC card creation. So until next time, that's it. Thanks for watching.